Okay, great. Okay, so we have the camera, very nice. Hello, and do you hear me? Yes. Okay, very nice. And you can your screen. I see that. Okay, I see your screen. It's working well. You can also try if this is working forward and backward. Great.
Thank you. Star clusters which have black holes. Star clusters have many other objects, stars, main sequence, red giants, neutron stars. So in our simulations we have all of them, but I will focus in this talk on the black holes because they could be sources of gravitational waves, and this is interesting since they have been detected with LIGO and Virgo. The team actually consists here of, here I have only mentioned the main collaborators. There are some more students involved. And this is a collaboration between Germany and China. I'm working in both countries, except for the last 2 years due to the COVID problems. But I hope that soon, sometime, I can go back and resume normal working mode. Now here you see just one slide about our working places. There's a big contrast. You see here in Beijing, the Kavli Institute for Astronomy and Astrophysics. It looks very historic and nice. It has been recently founded in 2008 only. It belongs to Peking University, where there has been an astronomy department many years before. And here my workplace in Heidelberg, my office in this quadratic, this rectangular building in the lower left actually. And this is a building which is is about 60 years old now, but the institute is much older actually. It is the Astronomical Computing Institute, and it was responsible for the calendar in the old times actually, and its foundation is more than 300 years ago. It was founded by a document of the Grand Duke of Brandenburg in Berlin in May 10, 1700. So this is a kind of contrast. So this is a structure of my talk. It's possible that I will skip some things depending on time. So first a brief overview of star clusters and their black holes and their gravitational radiation and detection. And then we come 2 chapters about very recent fresh research about the formation of larger black holes in star clusters, larger than usual, and about tidal disruption of stars, nuclear star clusters around supermassive black holes. So this is all related to star cluster dynamics. Codes and hardware are important tools, but I think today in this talk I will focus more on the physics. If you have questions, feel free to ask. This will be probably skipped. So this is our basic systems and our basic equations. So star cluster, typical example, globular star cluster 47 TAC, 1 million of stars, all have similar ages. But now the age is like 12 gigayears. The age is comparable with the age of the universe. And since stars have different masses, the massive stars evolve fast. And so they become red giants, and then they evolve they have a different color here in this picture. And some of them may explode in supernova, become neutron stars, or black holes. And here in this picture by Hubble Space Telescope, typically we only see the luminous stars. Some white dwarfs, yes, but no neutron stars or black holes can be seen here in this picture. And there is on the right-hand side, this is a zoom in. It's not new, it's just for explanation. This is an X-ray picture. And we see in the center of this cluster, which by the way it's a stellar density, it's very high in the center of these clusters. It's maybe 1 million stars per cube parsec. And if we would live in such a cluster, the night sky would be bright, because of so many stars. And what we see here in this X-ray picture is an excess of X-ray sources, more X-ray sources than we would expect in the galactic field. And it is believed that these are due to very tight binaries where there is tidal interaction and mass overflow and hot accretion disks around, typically something like an X-ray binary where we have a compact object and a more or less normal star, and then the accretion disk is around the compact object while accreting some matter. The accretion disk is heated and we see it in X-ray. And there are many more of these objects than expected in the galactic field, and that has something to do with the dynamics actually. And the dynamics down here, you see our main equation, and this is embarrassingly simple if we compare, like in the previous talk, magnetohydrodynamics. This is in the first glance embarrassingly simple equation. Just acceleration at some point, is the sum of the accelerations from all the other stars. Different from cosmological n-body simulations, we cannot make any approximations here because these star clusters are relaxing systems. The distant interactions are very important and must be resolved precisely. So we have really this kind of n-square problem, and in our code we also use the time derivative of acceleration. But this is a highly nonlinear differential equation, and everybody who is in let's say basic lectures on mechanics or nonlinear dynamics, you know what a trouble this can be. The solutions can be chaotic and can become unpredictable. So very tiny variations of initial conditions cause huge variations of the final result. So we have to deal with this, and my talk now today is not about this. I will just keep it at that and say that we are using a wonderful code which is called n-body 6++ GPU, which is based on Sverre Arsed's work, Gerald Hurley for stellar evolution, Seppo Mikula for regularizations and close interactions, Long Wang, my former students, for acceleration and parallelization, and I have been also accompanying this evolution of the code over the last, I would say maybe 20 years, yes. So this is now the introduction, what we can do with our code, what they call the Dragon simulation. It is the largest direct n-body simulation of a star cluster in a computer, as realistic as possible. And it is here in these two papers. It has been published. My former student at PKU, at Peking Uni, Long Wang, has been the main worker in this. And what you see here on the right-hand side is now not what the telescope finds, but this is what we get from our simulations. And you see there are pictures in the middle is what Hubble Space Telescope would find, like in 47 TAC. But we can, from the simulations, we can also separate. We know where are the binaries, where are the AGB stars. But most interestingly, on the right-hand side, you see we found hundreds of black holes in the cluster, stellar mass black holes, and they cannot be seen. And there was actually a controversy, a discussion whether such clusters, this is a dense cluster, but it is not extremely dense, it is not over dense. And many people believe that there should be no black holes in these clusters because they kick each other out in formation or dynamic reactions. But nevertheless, we find a lot of black holes here. So this was interesting. And here you can see, just for illustration, on the right-hand side. So this is what I said, our simulations contain all the stars. This is a color magnitude diagram. Magnitudes in Y and color as a proxy for temperature on the x-axis. And you see the cluster evolving in different times. We have here the 0 age main sequence, and then we just see the giant branches forming. And here on the right-hand side is a more resolved final state, 12 gigayears. We see the main sequence, we see how it is widened by binaries. We have a lot of very tight binaries which explain these X-ray sources. And here we see the white dwarfs, also the white dwarf cooling sequence as observed by the Hubble Space Telescope. What we do not see in this picture, again, is the neutron stars and the black holes. And in my talk now, I will just focus on them. Down here, you see just a picture of the supercomputer in Beijing. This was our own supercomputer in the National Observatory in Beijing, which we started in 2010. And it was what also partly brought me to China, that we have this possibility there in Beijing to run this cluster and start doing actually these large simulations using GPUs, by the way. And on the right is a gravitational wave signal from one of our merging binaries. I will just come back to this. Sorry, come back to this in a moment. And as I said, it has been a discussion how many black holes we would expect in star clusters. And we have been a team here which has for a long time actually predicted that there should be a considerable number of black holes, even in normal star clusters. Jonathan Downing was a postdoc in our team, and here are some papers from more than 10 years ago, where we just plot here the number of black holes in a star cluster as a function of time. And you see here at 12 gigayear, we still have actually, depending on the initial models, we have something between 100 and 200 black holes in our cluster. And we, at that time, remember, this was 2010 actually, before any detection, and we said we expect 1 to 100 LIGO events per gigaparsec per year. That was very early, and actually it was not an n-body simulation, it was something called Monte Carlo or MOCA. It's a simplified model, very fast, so one can do a lot of models. At that time, we couldn't do something like the Dragon simulations. And now later, so this is a paper here from 2016. This is just after the LIGO Virgo detection. This is the Northwestern group, Fred Razio and collaborators, and they also started running their Monte Carlo model after the LIGO detection. And so this gives you, so this is now 6 years later, yeah, and here you see as a function of redshift what they expected. They have some cosmological model, put some star clusters in different redshifts, and then they said here, this is what we expect, something at 0 redshift starting with, starting with a few mergers per gigaparsec per year. And then here, LIGO Virgo sensitivity ends somewhere here, yeah, around 0.2, 0.3, maybe going a bit higher soon. So we have like 10. And then when we go to higher redshifts, we end up at around 100 actually. And here's an error margin, which comes from mostly astrophysical errors about the knowledge of star clusters, of the initial conditions, their parameters. So you see, this is 6 years later, and still the final result is we expect something between 1 and 100, yeah, with a big error margin. And the origin, currently, we can only probe with gravitational wave detectors a very tiny region of these events, yeah, when they happen in the universe. And this is just here for your orientation. I just took here a plot where you see the look-back time as a function of redshift. So when we talk here about these redshifts, like up to 0.5, we are looking back to 4 gigayears here, and I think somehow LIGO Virgo, currently the most distant events, something like a look-back time, maybe 2 or 3 gigayears, yeah. So we are probing currently only this small fraction here. Yeah, and just for completeness, here is another paper. These are people more closely working with us, actually. This is still Monte Carlo models, yeah. So these Monte Carlo models here from 2018, and they also give here something like the merger rate normalized to the average as a function of time, yeah. And we are currently down here at 12 gigayears, and there we have something like 0.2 of the average. And also this paper is very clever because they keep the average as a free parameter, because we just don't know it actually. We have not enough star cluster models, and we don't know enough about star clusters at very high redshift in order to reliably say this, but it is still valid. This number 1 to 100 is still nothing more we can say, and I have to also disappoint you if you expect, you know, more precise predictions about LIGO detections. This general rate of events is very unknown currently, but there are some other things we can do, and I will come to this, and also interesting comparisons with real data coming from LIGO Virgo. Now, the first, before I come to this, a few words. So how do we predict gravitational radiation and detection from our simulations? Yeah. So I think I may skip a few slides here. I'm happy to leave my slides for download if you like. What we are using is actually called post-Newtonian dynamics. So we are not using full relativity because it doesn't make sense for basically two-point masses. We are talking here about black hole binaries, very tight black hole binaries. They have formed in our big Dragon n-body simulation, and now they begin to have relativistic interactions. The first thing happening is a perihel shift, like in our own solar system for Mercury. This is called Pn1 on Pn2 terms, and then when they come closer, the orbit shrinks, they start losing energy, and this orbit shrinking is connected with an energy loss through gravitational radiation. And there is an approximation called post-Newtonian approximation, which very well models this actually, and it has been compared with full numerical relativity simulations. And the idea is that the acceleration, dv dt, is here, and the lowest order term is just the Newtonian acceleration. This gm over r squared times 1. And then we have A and B, and these are different types of terms. We call them conservative because there is just only perihel shift, no energy loss, and dissipative terms, that's a gravitational radiation term. So this is how we add this to our equations for the n-body simulation, and then we know how our black holes shrink. And we know also how much energy is radiated from the shrinking of the orbit. And this is just an example from an old paper, where we just apply this and we see it in our orbit. On the left-hand side, you see a two-body system, two equal masses. The green orbit is just Newtonian. They orbit forever here in this eccentric orbit around the center of mass. And then we switch on the perihel shift, it starts shifting here, and we switch on the relativistic orbit shrinking, and the orbit becomes smaller down here to the numerical resolution. Here is the separation, you see the shrinking of distance as a function of time, and when they come close enough, like maybe 20 or 30 Schwarzschild radii, the time scale is so fast that we assume them to be merged. So this is what we are doing. And well, this is actually indeed, I'm often asked, how accurate is this post-Newtonian simulation? In the old times, one believed that actually from this post-Newtonian in spiral, which is well treated by post-Newtonian approximation, that there should be a chaotic phase until the black holes have merged, and then the ring down phase where the merger settles down. This is again something which could be modeled with approximation. But in fact, actually, numerical simulations, numerical relativity simulations show a different picture. They show, so this is, well, what is this? This is a gravitational wave amplitude as a function of time during such a spiral in and merger. And you see basically that the post-Newtonian in spiral reaches the maximum, and then it goes over into the ring down. So there is no complicated phase in between, and that strengthens the trust in our post-Newtonian approximation. And here, this is just a glance. I'm not going to explain all details of this picture. This is published in a paper. This is one example where we not only we have actually the energy radiated away as a function of time, but we have also a theoretical frequency spectrum. We look at our black holes and we determine at every moment of time the frequency spectrum, because they are typically on elliptic eccentric orbit, and an eccentric orbit has not only one frequency, it has a frequency spectrum. And this is here a picture of the frequency density as a function of time, and it is just going to the merger on the right-hand side. And this can be compared here. So what is plotted here is the same diagram. It's the first LIGO-Virgo observation. This is the final time. This is a fraction of a second. In our diagram, we were before, actually. We had several seconds before, so we were earlier, but we can reproduce the same data, and we can see where the black holes observed in LIGO-Virgo came from. So what is their history in this frequency, time, space? Okay, so this is now, I think I'm coming to the some new work actually. So this is inspired now by all the observations by LIGO and Virgo, which have been accumulated in the past years. In 2016 it started, and then more and more observations coming in, and what you see here is actually the mass of the mergers. It says, you can read this. Let's look here on the top of the diagram. There we have actually two black holes, one of about, let's say, 55 solar masses and another of 80 plus something, and they have been merging to something like 150 solar masses. And this has been very spectacular because it is in an unexpected mass range. It is in a mass gap, actually. Stellar evolution, here it's written up here, mass gap remnant with high mass, 142 solar masses. And the constituents from which the merger came, as observed by LIGO-Virgo, were in a gap where stellar evolution does not predict black holes. And this inspired us actually to run new dragon models in a set of recent papers. Francesco Rizzotto is a student at Max Planck for astronomy in Garching, who did here the main work. He ran a number of simulations, 80 simulations. Some, you see here some parameters with initial binaries, and the main thing is two things have been improved compared to the old Dragon simulations. One is we go here. You see this density profile, density as a function of radius, and some of these, this W naught equals 6 here, this black and red curves, these correspond to the Dragon simulations. But we have also some models which start with 100 times higher density and in between. So King models of index 9, 8, 7. So high density. And the other issue was there was a lot of work and a lot of upgrade regarding the stellar evolution. For example, stellar winds for low metallicity objects have been corrected compared to 2016. And also what happens when two big stars collide, actually. Some mass loss has been allowed in the process. And so I have no time to go really in the details. There's even one full paper actually describing all these updates. And ask me if you are interested in this. But these new simulations, they produced new black holes, actually. I told you the Dragon simulation, there is a lot of black holes, but these stellar mass black holes may be up to 20, 30, 40 solar mass black holes. But now, what we see here's an example, actually, from one of the simulations. This is a time axis here, from 8.7 to 84 megayear. And we see the formation path towards the mass gap merger. And So we have here some red giant and main sequence star. This all happens in the center of a high-density star cluster in the N-body simulation. They merge, they collide, actually. Yeah. Then here, this star here collides with a stellar mass black hole, which has formed from a single star, probably. And these two merge and form a 68 solar mass black hole. And here is another tree where already some stellar mass black holes have been formed, maybe from an initial binary, and they form a 70 solar mass black hole. And now these two come together and form a 140 solar mass black hole, and this is exactly so what LIGO, an object in this mass gap, a merger in a mass gap. And so here, these are the three papers actually dealing with these simulations, and our conclusion is this is no surprise. It's no problem for us to produce such a merger. If we have a star cluster and a high stellar density, we get these objects. And actually, this is only 84 megayears. They grew further, actually. They are possible seeds of intermediate mass black holes. Yes, and there are some, we find some objects as high mass as 300 solar mass. Yeah, so in a short time. I will skip this diagram and I will just go here. So this is our current best comparison with LIGO Virgo observations we can make. This is two plots actually. What we plot here is when two black holes merge, M2 and as a function of M1. Yeah, so secondary mass as a function of primary mass. So all events are below the diagonal. And then you see the detections are here, these yellow crosses, with some of them have very large error bars. And then you see our simulation points here, and left and right is two different approximations about the mass loss in stellar collisions. Yeah. So this FC equal 1 means that at stellar, when two big main sequence stars collide, they retain all their mass, and FC equal 0.5 means when they collide, they lose 50% of their mass. Yeah. So obviously, when they keep a lot of mass, we get here these high mass mergers, yeah, B and C. Yeah, but down here we get a good reproduction, I would say, of what LIGO Virgo observes. Yeah. So basically, the conclusion is that our star clusters in principle could reproduce all the field of LIGO Virgo observations. Yeah, it doesn't mean that all sources are from star clusters. There could be sources from the galactic field of other galaxies. Yeah, but it seems that our star clusters actually are able to produce here the main field, also some events in the main field, but also some high mass mergers which cannot be produced in the galactic field. Yeah, and here I just have plotted some of our high mass objects which are in binaries, black hole binaries, in a gravitational wave sensitivity diagram. And so this is the characteristic strain, the type of amplitude of gravitational waves as a function of frequency. And here are the sensitivity curves currently for LIGO Virgo, and then for several other instruments not noted here. Sorry. This is LIGO Virgo is on the right-hand side here at 100 Hertz. Yeah, and then this is LISA, future space-based observations. And in the middle are some projects which are called DESIGO, actually, for the intermediate range. And what we see, our most massive objects, they are very well observable by LIGO Virgo. This is low redshift. Yeah, so also the higher redshift would be observable. And then they shrink here, and finally, shortly before they merge, they come into the LIGO Virgo window. So, how much time do I have left? I'm started a little bit late, but how much do I have? 5 minutes, 10 minutes, 0 minutes? No answer. Okay, I'll try.
Okay.
How much?
Okay, yes, you have. Oh, very nice. Perfect. Go ahead.
Because I just want to show you one other field of activity of our team, and especially actually the Chinese part of our team. We have been using the same code, the N-body simulations, but we look for nuclear star clusters. And the only difference is that in a nuclear star cluster, we have a supermassive black hole in the center. We assume that it is already there. Yeah, so we didn't follow the formation, not yet. We assume it is there. And then we look for the interaction with the nuclear star cluster around. We have such thing in our own galaxy, yeah, such a nuclear star cluster, very well observed, but also in many other galaxies. And well, this is just here from our own galaxy. On the left-hand side is the observation, yeah, from these teams in United States and in Germany. And the Nobel Prize has been awarded recently about, just resolving this central star cluster and following the stellar orbits. And so we have started to do the Dragon simulation of the galactic center, 1 million bodies and a supermassive black hole inside. This is a 2019 paper here. And our student Taras Panamarev was here, the main worker. So this is kind of here a plot from the simulation. And here is just one result from this 2019 paper, but then 2019 paper. But then I will show some new results, very recent results actually. So this is here from the 2019 paper, where we could show in this million body simulation around the central black hole, we could show how the density as a function of radius evolves for different stellar objects. Yeah, because we have now the white dwarfs, the red giants, the main sequence stars, and the interesting thing here again is the black holes. The black curve is the black holes here. Yeah, and you see they become dominant here. More than most of the other stars, there is only here, this is low mass main sequence stars, is the other curve here, close to the black holes, and they are very low luminosity, they cannot be observed. Yeah? So the black holes are actually dominant over all the luminous components. And they follow also one of these typical power laws, and there are also binaries, and so this is there are two aspects here now. The question is what happens to the stars and the black holes when they come close to the supermassive black hole binary, a black hole, single supermassive black hole in the center. And there is something very well known as a tidal disruption event. It is here a standard picture from Rees in 1988. And the idea is that a star here passing close to the supermassive central black hole, here is on a parabolic orbit, and at the pericenter it gets disrupted by tidal forces, and half of the mass can be accreted to the black hole, and the other half has to escape for energetic reasons. And this lower half here, this is producing a high energy radiation event, typically in X-ray, and maybe also in some other spectral area, but mainly in X-ray. And it is believed that some of these tidal disruptions have been observed. A typical light curve has been predicted, which is not here on this slide, and I think I have it on the next slide. Yes, here. So this is actually a typical light curve of a tidal disruption here on the lower right, actually. And so there is something like luminosity as a function of time, and we get a very quick maximum, a sudden luminosity peak, and then it decays with a typical power law. Yeah. For highly eccentric orbits, a little bit different than for low eccentricity orbits. And here's also the dashed line. That's a standard for I think for the parabolic orbit, the E equal 1, and there is a typical power law decay which has been observed and which is searched for actually as a typical signature of a tidal disruption event. And now we have been modeling these systems and the number of tidal disruptions already in the 2019 paper. But now, the last thing I want to explain is now from this year, 2022, a just recently accepted paper where we have now adopted this tidal disruption scheme to the details of our n-body simulation. It means that every star has a different tidal radius, and moreover, we have a full and partial tidal disruption scheme, actually. What does it mean? It means here in this diagram, we look actually at different cases, actually. So one is here on the right-hand side, the normal tidal disruption, or also FTDE, which means full tidal disruption event. When this happens here, for a normal star, it is fully disrupted, and most of its mass accreted to the black hole. If it happens to a neutron star or a black hole, this is just swallowed without tidal disruption. But then we have here on the other side, we have actually a number of objects which we all have in our simulation. Remember this dragon simulation where we have the AGB stars and horizontal branch stars and many things. So a red giant, if a red giant comes close to the supermassive black hole, first its envelope will be stripped. And that is what we call a partial tidal disruption. And this partial tidal disruption leaves behind something like a core, a naked helium main sequence star, actually, in this case. And so this is our scheme here. I will not explain all the details, but the idea is that for these very extended giant stars, we have a larger tidal radius where the envelope is lost and a smaller tidal radius where the remaining object is disrupted, if it comes again close to the central black hole. And there are many interesting consequences of this. It's no time here to talk about all of this. You know, for example, about the deficiency of red giant stars in the galactic center. This is one way to explain it. But here, I just want to show one picture that before I come to the conclusion, and that is one of the results from our recent paper here. John Lee, Berzik, and myself in this year actually just accepted for publication, but not yet. It's just an e-print here available. And we actually looked at the rates of full and partial tidal disruptions and also at the observational signature. So this is just here the number of tidal disruption as a function of the strength of the luminosity, just in terms of Eddington luminosity. And we see here, this is the standard full tidal disruption here. This is a small peak here around very high luminosities. And here you see that the partial tidal disruptions produce many more low luminosity events. And nobody has looked for them yet, actually. So this is an interesting thing to look for them because they have a slightly different observational signature. So this is now about our clusters. I think I want to skip this. Just as I said, we are using highly accelerated supercomputers with GPU computing. The code, actually our code, is still the record holder for the largest n-body simulation with direct n-body simulation with direct resolution of particles. And here is my summary, which I will not read, but just maybe have some time for some questions. So thank you very much for your attention.
Okay, let's thank Rainer. Thank you for your interesting talk. Now we have time for questions, please. Okay. Yes, please. Dr. Haqi, please.
Thank you, Rainer, for very interesting talk. Do you hear me?
Yes, I hear you. Yes.
Okay, so my question is, yes, you introduced a possible cannon to form massive black holes in the star cluster. And my question is that how long, what is the time scale of the formation of such objects in the star cluster, and how long these objects can stay in the globular cluster or star cluster? I mean, do we expect to find such objects in globular clusters?
No. In most old globular clusters which are now around our Milky Way, I don't think we find such objects for two reasons. One is it's a selection effect. Those clusters which form these massive black holes, they have to be very dense and massive. And there is a very fast formation channel and a slower formation channel for the IMBHs. And when it forms very early, still there is a danger that it gets kicked out after some time. Yeah, and we don't have enough data to say something about this reliably. Yeah, the Monte Carlo simulations, they give some answer, but they are not very good for these small numbers of objects. Yeah, so I think we think we may find a few clusters. Typically, maybe the high density clusters. In some of them, we may find the intermediate mass black holes, but it is an exception for today's clusters.
Okay. Thank you. So we have another question, please.
Thank you very much. In your study, can you include the halo mass properties effect on the black hole merging? For example, the halo mass function or any different type of dark matter halos?
Dark matter, yes. Actually, in principle, yes. So far, we did not do it. Actually, we can do it. The point is, for the internal dynamics, when we look this innermost million stars, you see here is a larger n still needed because million is not enough. Still more something like 10 to 8 stars, and we get a good representation of the nuclear star cluster. In this region, the dark matter is dynamically not important. However, it is important for some of these questions, like the retaining the massive black holes. Now, when we have this dark matter halo around, these black holes, they get frequently kicked at formation time and also in Newtonian interactions. And when they is embedded in a dark matter halo, they come back instead of escaping to infinity. So this would be the next step. And Wang, actually, he has just a paper about these young star clusters where he added the dark matter halo around in a static way, and looks for these effects. So the answer is yes, it can be done. In our current work, it is not yet done, actually.
Thank you.
At the first part of your presentation, you showed a slide for the MOCA and the embodied state.
Yes.
That's the question. We don't have in MOCA, we don't have, for example, post-Newtonian term. And because we don't have such a formula. What we expect in systematic the Monte Carlo code in this budget simulation. When we are studying the black hole subsystem in the
actually, Mocha people are working hard actually to add this. You know, they have some special procedures for binaries. This is called BSE, binary stellar evolution, and this package is. We try to keep it as close to the black hole, to the n-body simulation as possible. We are very closely collaborating with Mirek Giersch and his team. But still, as you are right, it's not exactly the same. Yeah. So what they have is some orbit average shrinking, so they can include the post-Newtonian effects in some approximate way. And so we still, when we compare, there is actually some papers where we compare also, and there are still, when we look in detail, there are differences. Yeah, so this is still the problem. Yeah, we try to keep everything similar, but as I said, for the MOCA, in principle, MOCA is a statistical code in a sense. It uses average quantities of the system. It uses random numbers to put stars on orbits. And if in these cases, when we have these very massive objects, there are only a few in every star cluster. And so I think at the end, it's important to see what the black hole, what the direct n-body simulation gives us, but it is still very hard to do. Yeah, but we need the MOCA. Yeah, MOCA is not useless because we need the MOCA to cover the parameter space. Yeah, in their MOCA surveys they have, I think, a few thousand star cluster simulations, and they can tell us what are the interesting initial conditions. Yeah, so then we can actually start the n-body simulation and maybe at an evolved MOCA model. Yeah, so this is something in the future maybe.
Thank you. One more question. We can thank again Rainer. Thank you very much. And
thank you, and have a good day. Bye bye.
Thank you, and have a nice day. Hope to see you here at some point personally. Okay.
Yes,
have a nice day,
yes.
and thank you.
Yes.